Hi, everybody. You are on the Canada Wildfire webinar series. I'm Shalene Haynes. I'm the guest host for today, and I'm a wildfire research scientist with the Canadian Forest Service coming to you from Sault Ste. Marie, Ontario. I'd like to acknowledge firstly that the Great Lakes Forestry Centre, where I'm sitting, is on the traditional territory of the Anishinaabe, specifically Garden River First Nation and Batchewana First Nation, and is on the lands of the Robinson Huron Treaty, as well as the Métis people. This land, Bawating, meaning place of rapids, is a historical meeting place for Indigenous peoples from across North America. So just a couple of housekeeping items before we get started. This is being recorded as well. Once the presentations are done, questions can be entered in the chat, and hopefully we'll have some time to pose those questions at the end. So today we have three of my CFS colleagues with us to talk to us about the recent paper that was published in Global Change Biology, mapping the distance between fire hazard and disaster for communities in Canadian forests. So we have Sheng-Li Wong from the Northern Forestry Centre, Tom Swiston, who's here with me at the Great Lakes Forestry Centre, and Colin McFadden, who's also at the Great Lakes Forestry Centre, but in Dryden. And so with that, I'll let these guys take it away.
Okay, excellent. Thank you. Harry, good morning, everybody. Today we are going to present a recently completed project, mapping the distance between fire hazards and the disaster for communities in Canadian forests. Canadian fire researchers have been noticing that fires don't grow in random directions in the Canadian forests. And this has been kind of a phenomena we noticed for a long time. But right away, we would think, what about those fires close to the community? Would those fires coming in the community with certain directions instead of in a random manner? But with the historical records, we don't have enough of the sample to do anything for all the communities. And this has been changed until we have been working on this project, which is mapping wildfire hazard, vulnerability, and the risk to Canadian communities. This is led by Dr. Sandy Ernie from the Great Lakes Forestry Center. And in this exercise, because risk, in order to assess risk, we have to consider two major components. One is the fire hazard, another one is the physical vulnerability. So fire hazard, in order to assess this, we need to assess likelihood and intensity. So what we did, we used in order to achieve this this goal, we used the fire simulation model. This is called BURN-P3 to do the job. So BURN-P3 is a fire simulation model. It combines the stochastic aspect of ignitions, weather, with deterministic fire growth model technique. And basically, the model will ignite multiple fires for a given year and grow those fires. And then we repeat this process in a Monte Carlo-like process. After thousands of iterations, we try to burn the landscape in so many different ways. Then we tally the number of times each pixel were burned, divided by the number of times we burned the landscape. And then we have this so-called burn probability with the likelihood of fire. And this process will also produce other fire behavior parameters and measurements. So basically, it's a fire ignition and fire spread simulation process. So for the fire spread, we rely on a fire behavior triangle algorithm, with including weather, topographic, and fuel. And one of the a few of those outputs would include the fire spread rate and fire intensity, and also we could preserve the simulated fire polygons. For fire ignitions, we consider two components. One is how many fires each time you burn the landscape. That is the number of fires per year. And those are obtained from the historical records. It's a distribution of number of escaped fires. For where fires actually ignite, we use this so-called ignition grid. And this is something you could use a different technique to do this kind of thing. And for the fire spread part of the game, the field was recently developed by Steve Taylor and a group of people, including Thomas Whiston, who was the coding expert behind it. And currently, of course, we have a newer version of this field layer, but back then this was the best at the moment when we were using it. Topographic, there's nothing to say, it's DEM. And for weather component, we use weather to control how long fires actually burns. That is going to modify, the fire sizes, and eventually annual error burn, those kind of parameters, make sure that burn P3 would mimic historical and the fire regime situation. Another part of the simulation is daily fire weather conditions. So this is required from FBP fire prediction system developed by the Canadian Forest Service 20 years ago, still used in our community. Without those, we were able to produce a bunch of fire behavior related besides burn probability. We have a bunch of other parameters, including those fire polygons and rate of spread. These two components are crucial to this study. For the fire parameters, we use this to define fireshed, and also it will constrain the fire pathway for where fire actually would grow. Rate of spread is the speed of how fast the fire goes. That is important to measure the distance between fire front or fire advance perimeters and to the community. And also it will decide how fast the fire pathway could go or where it goes. So to proceed, because we are talking about fires around the community, so we have to define a concept. This is not a new concept, but we adopted this from others. This is called fireshed. Fireshed is the area around the community from which a fire could ignite and spread to that community. And it is similar conceptually to a watershed, that all those waters will converge at a certain point, like the river mouth, For the community, the location all these fires would convert, means all those fires would eventually burn into the community. That's how we delineate the fireshed for each community. This example on the right is Red Lake from Ontario, and we basically kept the simulated fires that overlapping with community boundary, and outside the outer perimeter is going to be the extent of the fireshed. And we did this for 1980 communities in the foresty area of Canada. So because of this project and the National Fire Risk Project, we could do this kind of work. And clearly, after we have those fireshed mapped, and then we started to do a little bit of summary statistics, how big are those firesheds? You know, from this table, you could see in certain Canadian ecozones, some of the firesheds are super big. For example, the maximum in one of the BP is the boreal plain is 24,000 square kilometers. That is very large. And we also found that the fireshed size are bigger in the northern ecozones than in the south. But measure it from a different perspective, the distance between the perimeters and the community boundary, we will see most of those northern ecozones, they have a larger distance. Of course, their area is bigger. Certainly, they are bigger in terms of the distance. The number of communities, some of those ecozones are smaller, and they don't have a lot of communities in them. But in the southern part, there are more communities that we suspect is a little bit more, fire suppression and more fragmented landscape. That could be the reason for the size differences among those communities. And as I said at the beginning, so we were interested to see the direction of whether fires come to the community are from certain directions or not. So instead of just random coming from every direction, so we did a test. It's called let me see what's it called. Called a relay Z test. You cannot ask me how it does. I forgot already. But it will give you statistics indicating whether the direction is significant or not. So by ecozone, we found about more than 70% of the 1980 communities that showed significant directional fire burning into the community. They don't burn around the community, from everywhere, from certain directions. And that means it is close to 1,400 communities in Canada that has this kind of a pattern. By lightning itself, the proportion is a little bit smaller, so close to half of them. And human-caused fires are sort of more directional. It is close to 70%. And this is a demonstration for what kind of a direction we are looking at. So for some of the ecozones, the directional trend is quite significant. For example, the boreal, the BC, where's the BC? Let me see. BC is boreal cordillera. So northern BC and the Yukon, that part of the country. About 50% of the community show SSE as a direction fires most likely to burn into the community in that direction. And for a few others, especially in the mountain areas, the strength of direction is not as strong as those in the boreal plain and the shales. This is a summary for the generic part of the study. I'm going to turn over to Tom, who is going to talk about the more interesting and more important part of this study. That is the distance between fire progressing front to the community boundary, and also fire pathway, fire corridor, how those were developed and mapped, and what they mean. It's yours.
Thanks, Shenley. So in the next slides, I'm going to walk you through some of the methodologies developed in this paper linked to rate of spread. So underlying the majority of the methods I'll be presenting are the landscape rate of spread layers. One of the outputs of burn P3 is rate of spread, measured in meters per minute. And a distribution of rate of spread values is generated for each pixel in the landscape based on the number of simulated fires affecting that pixel. So for example, if a 250-meter resolution pixel is burned by 50 fires in simulation, there will be 50 rate of spread values logged at that pixel location. So for each pixel, we then extract the median and maximum rate of spread from this distribution, resulting in median and maximum rate of spread landscape layers for the country. Median rate of spread was chosen to represent the general conditions, while the maximum rate of spread was chosen to represent extreme events. It's important to note that real-world rate of spread may vary for any actual fire in both space and time. So in Figure B, we show the 1,980 communities of interest for this study. We limited our analysis to communities with populations of at least 200 people, as many communities with less than 200 people were found to be temporary or abandoned settlements in a previous study. To describe the methods, we chose the example community of Red Lake, Ontario, which is located in northwestern Ontario and is represented by the green star. We chose a Canadian ecumene layer to represent the community boundaries. The ecumene is delineated based on nightlight imagery and is a systematic buffered representation of Canadian communities. Okay, so what can we do with those rate of spread landscape layers? Well, the first thing we did was try to develop isochrones. So what is an isochrone? It's a line drawn on a map connecting two points at which something occurs or arrives at the same time. You can think of them in the same way that contour lines connect points of equal elevation, but instead of connecting points of equal elevation, we're connecting points of equal time of fire spread from sources to sink. So we use an accumulated cost surface function to calculate the time in minutes it would take for fire to spread from each pixel within the community fireshed. In these figures, the fireshed is represented by the purple line, and to the community's boundary, represented by the ecumene, which is the red line, through the shortest cost path, where cost is represented by the rate of spread landscape layer, both median and maximum. So the pixel is the source, the ecumene is the sink, and the cost of the source to sink is through the rate of spread layer. The output of writing the accumulated cost surface function is a cost surface layer, where the value of each pixel in that layer is the time in minutes for fire from that pixel to reach the ecumene. This layer is not pictured, but from this layer, we can then apply a contour function to connect pixels of equal time, giving us our isochrones in 2-hour increments around the community. In comparing Figure B and Figure D, you can see that as rate of spread increases from median to maximum, the isochrones are further spread apart, showing how at higher rate of spreads, fire takes a shorter time to spread further distances. Next slide, please, Shenley. So to analyze these isochrones for each community, the distance was determined from which a fire could spread to the community in 1, 2, and 3 days, using maximum and median rate of spread. The number of hours of burning per day were independently determined for each modeled unit within the burn P3 simulations. In this example of Red Lake, the number of hours of burning per day was 4 hours. Excuse me. The figure shows the day 1 to 3 spread and how we measure the distance from the ecumene boundary to the daily spread perimeter in 5-degree radial transects. Across the country, the average 1, 2, and 3-day spread distances are approximately 5, 12, and 18 kilometers respectively for the maximum rate of spread, whereas for medium rate of spread, they average approximately 1.5, 3, and 4.5 kilometers respectively. We found that these 1 to 3 day spread distances increased from the south of the country to the north. Okay, next slide, please. So another thing we can do with these rate of spread landscape layers is to map fire pathways. So a fire pathway is the fastest route measured in minutes by which fire may spread from an ignition location, which is a source, to the nearest point on a community ecumene boundary, which is a sink. Is not necessarily the shortest route in terms of distance. We use an accumulated cost surface function again to calculate the fastest path from the initial location of each simulated fireshed fire to the nearest point of intersection between the fireshed perimeter and the community ecumene. The pathway was constrained to stay within the perimeter of the fire with the rate of spread, either median or maximum, as the underlying cost layer that guides the pathway. Breaking this down into its individual steps, first we have figure A, which again shows the Red Lake ecumene and fireshed with the median rate of spread landscape layer in the background. The gray polygon represents a single fireshed fire, which again is a simulated fire that intersected the Red Lake ecumene. In figure B, we zoom in on that fire and mask the median rate of spread landscape layer with the fire polygon. The ignition location of that fire is the black asterisk. In figure C, we see the least cost pathway or fastest pathway from the ignition location to the ecumene through the rate of spread layer constrained by the fire perimeter. Now, if we repeat the same process for all simulated fires, and because we're using the same underlying cost layer, we begin to see a convergence of these fire pathways, which gives us next slide, please, Shenley. Our fire corridors. So a fire corridor is a common channel shared by fire pathways that converge towards the same sink. Fire corridors highlight preferential routes by which fires may spread towards a community. To create the fire corridors, we first dissolve all the fire pathways that we created into a single feature. We then split this feature into segments, where each segment represents a unique line between junctions and/or endpoints. The density of fire pathways that traverse each corridor segment was calculated and expressed as a percentage based on all pathways. The simulated fire corridors can be seen in figure B and figure C for median and maximum rate of spread, respectively. But as fireshed fire ignitions tend to cluster close to the community because of human activity, we want to map the fire pathways and corridors for all possible fire ignition locations within the fireshed. To do this, we randomly seeded the fireshed with hypothetical ignition locations spaced approximately 1 kilometer apart. This is in figure D. Using the fireshed boundary to constrain the fire pathway routes, the same procedure was followed to build the seeded corridors as the simulated corridors, which can be seen in figure E and F. In comparing the simulated to seeded corridors for Red Lake, simulated fires tend to burn into the community from the southwest. But as we can see from the seeded corridors, there is a lot of potential for fires to burn towards the community from the north and east as well. It can therefore be reasoned that fuel connectivity isn't the limiting factor in the Northeast, and that the spatial distribution of fire ignitions and weather patterns play an important role in determining the direction that simulated fires will most commonly enter a community. Next slide, Shelly.
And I think it's over to me.
Yeah, Colin, thanks.
Thanks, Tom. So what does all this mean? The good and the bad, especially when we're thinking about management implications of using modeled and simulated data and that type of thing. I'm going to preface all this by saying, of course, any kind of risk assessment requires, in my opinion, field level data and a lot of different sources of data. But we're going to talk about this method and some of the insights that one might draw from it. And there's some good examples, and there's some not so good examples, and we need to be really transparent about what these things mean. I'm going to talk about this more as a methodology than an output. So think of what was just presented as these are things that can be done with, we have to think about the data latency and the data resolution and what the best sort of fit is. And this type of approach can be rerun and redone for different cases. But let's go to the next slide here and take a look about what I mean by the good and the bad. Oh, I don't know if there's a lag, but next slide, please.
Just a moment. For some reason, oh, okay, it works.
There we go. So we put some examples together to just sort of give a bit of a narrative explanation of some of this stuff. So here's a 2023 case with Yellowknife. So that's the Yellowknife community there. The red is the boundary, and that green hashed area. So that's the M3 fire perimeters that's made of consolidated or connected hotspots. And when you look at the corridors that are drawn as the sort of preferential fastest path, and you look at where the fire is, there seems to be some visual association. At least it looks like the two arms of the fire that are spreading or that are presenting towards the community tend to be corridor connected visually, like no statistical tests or anything like that. But we wanted to see how this played out in the real world. So Tom made a fire progression map, which is the one on the top right there. And those are Julian days in the color. But what you can see is the fire did start from outside of the fire shed, burn into the fire shed, and somewhat follow those preferential routes. So this is an indication that this seems to follow what the simulated world had presented. But let's look at the next slide. There are cases where this doesn't happen, and this is something that why you need to look at this. Any community level assessments need to be done at a community level. So one of the things we presented this to a group of fire managers to get some feedback on the concept. And Laurent here in Saskatchewan was one community where the underlying modeling, like Burn P3 and the way that it handles past fires and converted fuel types, it actually constrained the fire shed to not go to the north, both by water features and by historical burns. So what you see here is when you apply the method, what we're told by the experts in Saskatchewan was in this community, fires from the north tend to be the concern and like historically were the largest problems. And they're really underrepresented in this methodology here. So being able to go through this with people who know the area and look deeply at what the data is saying and what it means is a requirement to know whether it's something that is appropriate to use for informing some risk assessments. So let's go to the next slide, please. Stressing that in fire operations, of course, when a fire is on the landscape, you're dealing with real forecasts, and F-bands are doing their things, and you have actual fire models to look at what's going to happen in the next 5, 10, 15 days or whatever. When you think about corridors and the fire sink and fires, the preferential route towards a community, that's sort of strategic level planning. And this is just a really good example. So this is the Soyuz in 2023 as well in British Columbia, and where the fire starts close to the community and then burns, in the opposite direction. Suppression action, of course, all these things are influencing the shape of that fire. But this is just an illustration that, the pathways aren't necessarily an operational tool, but they might provide some insight into strategic value on what mitigation efforts might be done for sort of these preferential routes. And that's, I think, what I'm going to talk about next with the next slide, maybe. Oh, not quite yet. Extending this idea of what, no, go to the next slide yet, but I'm not going to talk about mitigation. So one of the insights here that we thought about is the fireshed concept, right? And the potential to one of the questions that protection zones around communities, that kind of thing, especially for communities that are remote and hard to access. one of the typical approaches is, there's some boundary. Once a fire starts within it, or burns into it, that's when action starts to take place. So what we wanted to illustrate here was this concept of fireshed, and whether in a simulated environment, sort of the size and shape of that fireshed is something that might be considered, versus like a historical process of putting a 16 kilometer, 10 nautical mile circle around a community, especially considering some of those directional preferences that were spoken about earlier. So this is Red Lake again here, and what you're seeing in the background is all the historical fires from 2012 to 2023, and it's a mix of NBAC data and the M3 perimeters, and the point data of fires for the smaller fires that don't become large fires from 2012 to 2022. So Red Lake has a lot of fire around it. And what we see is, of the actual fires, does that buffer seem like an appropriate, that fireshed seem appropriate? And then the bottom right are all the simulated fires and the ignition points for those simulated fires that made that buffer in the first place. So it's just another way to possibly think about a method to revisit the idea of protection zones around communities and that kinds of things. And of course, considering some of the other standards that are out there, like Fire Smart and whatnot. Let's go to the next slide. I won't get too much into the technical stuff here. I think this is still my slide to present. I think that the take-home message is, of course, the motherhood statement: any risk assessment around communities has to be done at the community level, using the data that's appropriate. This is what we've demonstrated here is a method that could provide some insight to the folks that have to do this kind of work, and it may provide strategic insight on preferential pathways for communities to consider things like mitigation. It can talk about the directionality, where there are some communities and some areas across in ecoregions, there's a predominant directionality either through weather, ignitions, and that type of things that could be considered to help prioritize areas. What else do we want to say here? Rerunning this method, addressing up-to-date data, burn P3 runs, whether the 250 meter resolution is good enough. These are all things that need to be discussed before one starts to think about how can I use this in an operational way. And this method and some of these results, along with all of the other things that are out there that can help inform decision makers, it's really important to think about risk as a constellation of models versus sort of one to rule them all type of thing. So this isn't a silver bullet for anybody working at a community level by any stretch of the means, but it is hopefully a method as well as some results here that can provide some insight to the folks who have to think about these things. And Tom and Shing Li, in case there's anything else, I'm going to hand it back to you guys.
Thanks, Colin. I think that's it. That is the whole presentation. I'm going to stop sharing, and we can. I think we have time to take some questions.
Great, thanks, guys. If anybody has any questions, can you please enter them into the chat? Yeah, I read through your paper. I quite liked it. I did appreciate at the end, Colin, when you guys did some validation, because that's one thing when I was looking through stuff that I was kind of thinking about is, because and you did a really nice job too at the end of the paper and in the talk too, talking about some of the limitations, because this is based upon climate, previous climate, not necessarily so predominant wind directions, things like this. So there are events that might happen that we aren't necessarily anticipating. And looking at those pictures of Red Lake, I was thinking about Kelowna and how Red Lake, you got that lake there and nothing came through, nothing's coming through where you got that lake. But, if you were to do this for Kelowna, keeping in mind though, the FBP and the inability to spot the distance that did, maybe the restriction, but can we start to poke holes in some of these models that we have lined up to do this? I'm just interested in any further thoughts on that.
Yeah, I think you hit the nail on the head there. And in our paper, we did do a fairly thorough job on the limitations section, but spot fire is a massive one, right? Like in these simulated environments, because fires can propagate kilometers ahead of themselves, and these landscape water features that block a burn P3 run in the real world, they might not. And that's exactly what you saw in Kelowna. And I think we did look at some examples of Kelowna and how it, our methodology fared in the real world. And these are the cautions that we give about operational products versus strategic thinking and informing like a broader risk assessment process that this feeds into. It's really important that we keep that top of mind. I don't have anything else technical to get into there. There's lots of buttons to think about, and each one has a limitation.
Yeah, I think some, did you, and those validations, are those in any of the supplementary material, or is that just something that you did afterwards?
We did upload those data in archive. So if you go to the publication, you can find all those layers for 1980 communities, and they are GIS shape files. You could check the communities with your interest.
Cool. Mike Flanagan has a question here. How sensitive is burning period? Can you change the 4-hour burning period based on the historical weather?
That is a really really important question and interesting question. So burning period in the southern part could be 4 or 6 hours. In the northern part in the summer could be even 8. So this 4 hours is just we use one. This is the most commonly used in simulation work we do. So from historical, hopefully in the future we could actually model based on the historical records. Not only that, remote sensing monitoring detections, and eventually we could model it.
Sorry, different hours of burning per day are accounted for within the simulations. So the Northwest Territories, it's up to about 6 or 8 hours per day based on the season, and in the southern Canada, it's lower, 4 or 6, as should be said.
So those numbers were in the simulation we used.
I'm curious because it says it's my name that put this, but I didn't type this, but I have a question about the calculation of likely fire spread pathways. Are these based on least resistance, such as rate of spread paths? And there's a couple parts to this. How well do the estimates of fire spread paths agree with the local fire spread paths within the simulated areas? And did you try to validate the fire path well, we just talked about, but yeah, further to that, did you try to validate the fire path calculations? I don't know if you guys can see that in the chat there. Who wants to take that one?
Can you go for it?
Hmm?
Yeah, I'm just reading it here, please. So for the first question, are these based on least resistance, fastest rate of spread paths? Yes. But as I mentioned before, the landscape rate of spread rasters are based on all simulations, not just how that one fire burned through. That's how we get the convergence. If we did it with just the single fire and did fire paths for each fire with only the area that it burned at the rate of spread that it burned, we wouldn't find that convergence. So the rate of spread landscape raster gives us a general trend on the landscape for fire spread.
But Dave's question, any correlation of pathways with fuel types? We didn't check those, but you would assume that conifer would, with a strong wind, the fire would move faster than in Miswood and Broadleaf. When we so this is as what Tom just said, the pathways and the corridors were based on simulation rate of spread. We just wanted to know what is the quickest way for fire from ignition move into the community. So basically, it's kind of like a worst scenario, worst of the worst scenario. So approach.
I'm gonna jump in here, and I'm not technical, so you guys can stop me totally. Everyone's like, oh, Colin's gonna say something technical. To Dave's question, I think that's a really good question. Because it's a landscape rate of spread surface that's made up of fires that were simulated in the springtime, in the summertime, and the fall. You know, and the fuel type association, you can think that there's different fuels that behave different, but they're all, you know, they're all sort of put together as the worst through the simulated environment. So some of the fuels that burn the most volatile, you know, there is a seasonal component to it, I'm assuming. So it's not, it's an area for refinement to dig down into to see, you know, if there's seasonal aspects, that kind of stuff. But this is like Jamie said, it's more of a worst case scenario of all of the worst rates of spread in the simulated world that, you know, for the maximum rate of spread and the median are sort of, you know, comprised of all the simulations, different times, etc. That makes sense.
Yeah, we didn't have the ability to look at this seasonally, but in future iterations, that's definitely something to consider.
Okay, so I just have another question here. For members of the community, is it possible to get the information that would be applicable to that specific location? Okay, so that, Shailene, did you answer that? Specific locations rather than looking at the large scale maps? Is that what you're?
Yes, we do have those 1980 community uploaded in the archive. So go to the paper, you can find that link and download any community you want. But that being said, as what Colin just mentioned, that this work is based on some outdated data up to 2017. As we remember last year, we had 15 million hectares burned across country. A lot of those are wildfire. They burn into around those firesheds. Our estimate are not going. Some of those are not going to be as accurate as they should. So we need to update the the burn P3 model run at least. So we are making the effort from East and West right now. On top of this, I saw Dave Schroeder also ask a question: what we are going to build upon this? So this is based on the national fire risk assessment mapping project. The data resolution accuracy, a lot of those are not detailed enough for a specific community. So we are working on. We are trying to figure out how to work on the community level, more detailed, more reliable kind of procedure to do the same thing. Sandy, Ernie, and Tom, they are working in the east. I have a big group with Tom and Sandy in the west. So Northwest Territory, we are going to work there for 3 communities. Hope this answers your question.
So we have another, first a comment. Thank you guys for the presentation. And then specifically to Yusheng Li, you presented a slide that looked to have several wind roses showing directional trajectories for fire. Can you briefly go over the methodology for developing the wind roses?
That is just directional. So from the simulated fire, the fireshed fire, the fire that overlapping with community outlines, we draw a line between this and the community centroid. Basically, we want to know where the fire initially are from, eventually burn into the community. That kind of direction, and with all those directionals, all the directions, every point, ignition point, there is going to be a direction. And then we just plug into a statistic test. It's called always forget that relay, RAYLEIGH Z test. If you go to my that publication, actually we wrote down all those formulas and equations in the paper, so you could apply it yourself. And if you want to have some R codes, talk to me and Tom. We have something in our computers that we can share.
Thanks, Shirley. Another question, is there an existing map that shows the location of each community within a population of 200 or more?
I could answer this one. So with the Canadian Ecumene is a product developed by Brian Eddy with CFS. If you search Google it, it'll come up. I believe it's current to the census population for 2016.
Great, thanks, Tom. Another question that says me, but I'm pretty sure it's Dennis Yemshinoff because I sent him the link to I'm like, how am I typing this stuff? And it's not me. Anyway, okay. So the fire maps show the fire spread paths concentrating to very narrow channels as they approach forest communities. Are there any ways to verify this behavior by historical fire spread data?
Colin, can you answer that? You know more than I do.
Oh boy, remember the whole non-technical part. So fortunately enough, we don't have a huge population of fires that actually burn into those community zones. There's a couple of case studies, and I think we picked a couple there to show. So the short answer is the data to do a validation with actual fires that burn into the zones is no. And the simulated world that we're trying to get at to here, without refining the data to have each rate of spread from the individual fires, instead of using that surface, that would be the part that we would need to get to do, the kind of validation of the individual fires and the rate of spread of each fire independently. But that is not what we had the data for, frankly. An area for refinement for sure.
Yeah, maybe some data like some fire progression maps that could, that'd be a case by case.
Yeah,
but an interesting one for sure.
Absolutely, and Tom showed a couple of really good examples there from 2023 that we could likely dig into a bit more.
Yeah, I think it'd be super interesting to figure out where the hole, where are the holes? Is it coming from, base, the engine at the base of it from the FBP, or is it coming somewhere else along the line?
Yeah.
Methodology. So another question here, maybe this is mentioned in the paper, for the rate of spread and the path of least resistance. Does it account for the daily seasonal changes in wind speed, wind direction, in addition to landscape/fuel?
I can take a step on this one. So it is basically burn history. So in burn history model, the fire weather part, we do consider wind speed, wind direction, along with other FWS system variable as input. So when we simulate the fires, we do have this seasonality embedded in the burn history run. Because of this kind of modeling approach, all those simulated fires should involve wind speed, wind directions, and daily seasonal changes. So it is in a way not directly for our project, but it's indirectly we consider that. I think. I hope I'm answered the question.
Thanks, Shane. Someone had posted that link to the Canadian Ecumene, and then there was a comment about for small semi-remote First Nations communities that they work with, only one reserve is represented in this data set. So caution for using this for small spread out communities. So something maybe also to look at potentially in the future and to keep in mind. Thank you for that. Another question here, if the community is located near the US border, is there a way to get the information for the community which is across the border or in general other countries?
I'm not sure, Tom, do we have one?
The simulations buffer 15 kilometers into the US, but the data into the US is not as reliable. It's basically just to give us to address edge effects with the modeling procedure. That's why we do the buffer. So no, but the methodology is available. Certainly, I'm happy to share any scripts I have if you want to apply this to an area that you're interested in. To address the previous comment, while we, in this data set, we did keep it to communities greater than 200, we have applied this to smaller communities that had specific interest in this product. So if you want to get in contact with us, we are happy to run those communities through for you.
Maybe, Tom, you guys want to put your emails? No, that's a good idea. Not going to put your email in the chat. People can chat with you further about it. So another comment here, great work, impressive visuals. To build on Kelvin's question, communities would find significant value here for local evacuation mitigation planning. Many lack sophisticated GIS capacity. Any potential for follow-up efforts to centrally provide these for communities? I'm assuming that's kind of what you were just saying, Tom, along those lines?
Yeah.
So there is potential to be working with individual, and you already are kind of working along that line. Okay. There was a study published last year that also looked at community vulnerability based on wildfire direction. Did you collaborate with those authors to build off that work? Are there plans to work together to further this model?
So we are aware of that work, but we weren't because it is a parallel kind of efforts. We were doing the job, and the team published their work already. So there's not real conversations between each other. We did read their papers and set their papers, and for the future, we will see. At the moment, we don't have plan for that.
Well, I think that they're like you guys discussed, and you mentioned this isn't the model to rule them all. So I think the more, variety we have in different methods and in different models, I think that brings us strength in that, looking at each, because not everybody's going to cover the same thing. So, and we want to have a number of models out there so that we're looking at things differently, and that if one is missing it, that maybe something else is going to pick that up, so that we have more strength in numbers by looking at things in different ways. So I think that that's a good thing.
That's
exactly. It would be interesting to see where these models where they agree, and just as importantly, where they disagree and why.
Yeah, because you don't want to be left where you have that, we talked in the past about those black swan events, those events that you don't necessarily predict, that may not be following that predominant wind direction. And with climate change, we've got extremes, we have shifts that are going on, so things that can pick up where we might be missing, I think are really important. Okay. Anybody have anything more to add on that? Okay. If not, is there a way to find the recording of the meeting? I'm assuming that will be on the Canada Wildfire site. Renee or Emily, if you could.
Yep, that's right. I was sorry, I was just typing a comment and couldn't find my unmute button in time. But yeah, that's right. So we'll post it on our Canada Wildfire YouTube channel. And we'll also send the link out to all of the attendees afterwards as well, as soon as it's available.
Okay, excellent.
Thank you.
I'm not seeing any other questions in the chat. If anybody wants to add them quickly. I did have one quick question, guys. I was just curious about, I was interested to know lightning. Does lightning have spatial patterns, lightning emissions?
It depends where it is. So Mike could have a better answer on this. In some of the areas, you do have this kind of lightning shadows, that lightning never strike that location in the Rocky Mountain somewhere, and some other locations might not. Is here.
Hello. Yeah, I'm Mike Flanagan, and yes, there are definitely lightning patterns. And there's been a lot of work done in Alberta and British Columbia in the last few years. Sean Coogan, Olivia Aftergood, both have papers. I'll try and post them in the chat. But yes, there's definite spatial patterns to lightning activity, which I think burned P3 calculates in their ignition grids? Tom or Shang-Li?
Yeah, so ignition grid covers part of it.
The historical patterns, yes.
Yes,
Yeah, there are-
we do ignition grids with historical patterns of lightning.
Yeah, that's what made me think about it. But I liked how you did, that, and then you also did the random. I thought that was good. But yeah, maybe I wasn't aware of that, so I was curious. Okay, yeah, lots of comments that this is a great webinar. I completely agree. I think it was awesome. And yeah, anybody have anything else to add before we sign off?
Thanks everybody for coming.
Thank you.
Next time.
Thanks, everyone. Take care.